Okay, so the last couple of yesterday's two talks fed into each other. This was the story of adding more and more structure to monoidal categories, and if I'd allowed that material to take 3 lectures instead of 2, I would have probably done a better job. But I wanted to use the last talk to talk about some stuff that's closer to what I work on. And a couple of people mentioned they're excited for this, so apparently this was the right choice, but it's collectively our fault that the last 2 lectures were very, very condensed. So that's that's the trade-off. So I'm going to talk about lenses and bidirectional processes. So, okay, maybe it's worth saying a little bit of intuition for how I think about the kind of monoidal categories that arise in applied category theory. As a general rule, I tend to mentally divide the categories that we have in applied category theory into process theories and systems or network theories. This is a purely informal distinction. It's sort of, you know it when you see it kind of thing. But so as a general rule, a process theory is something, I mean, it's so your morphisms are some kind of process. So they're a thing that takes some kind of input and gives some kind of output, and you sequence them. So basically, when you draw string diagrams, say left to right, this direction is actually time in some physical sense, and then this direction is space. So I say these things are time-like, but there are also, so for example, the categories of open graphs, the structured cospans of graphs. This is not time-like. These things are not processes running from the left boundary to the right boundary. They're purely spatial. So there you have space both ways. So it's really 2 spatial dimensions. So this is pretty informal, but I tend to make this distinction. As a general rule, things which are space-like in both dimensions tend to have more structure, like they're compact closed hypergraph, because you can just twist. Like if you have some kind of physical wire or physical connection, pipe, whatever, you can actually just bend them around any way you want. There's no requirement coming from nature that things have to be oriented in one particular direction. Whereas when you have a process theory, you really get some kind of causality constraints coming from nature that, like, some things have to happen before some other things can happen. So as a general rule, they tend to have less structure. They tend to be merely monoidal or maybe traced. If they have some kind of feedback. But again, this is a purely informal thing. I can't define these. Also, the category of quantum processes, like the things that you can talk about in ZX calculus, is a big exception because they are process theories. They're sequences of steps that you apply to a qubit or a bunch of qubits one after the other, but it has all of the structure that I associate with space-like things. So that tells you something maybe deep about quantum theory. I don't know. By the way, if you read pretty much anything introductory by Bob Kirker on categorical quantum mechanics, you'll see his diagram for quantum teleportation is this is like so you have a kind of space-like separation here, and one party creates a couple of entangled states and then transmits one to the other, and then this one can send a message instantly from here to here. Okay. But anyway, so all of that was to build up to everything I'm talking about in this talk is about processes. So things which are oriented in time, but in a much more subtle way than being merely left to right like functions. So let me make the first main definition. So we have a category called lens. Is a category where, so the objects of this are going to be pairs of sets. And morphisms from the pair x prime to the pair y prime are going to be pairs of functions where f is going to be a function from x to y, and f prime, this is going to be the weird one. So this is going to be x times y prime to x prime. So this looks a bit like the category set times set up. We have like a function from x to y on the top, say going forwards, and then we have a function from y prime to x prime going backwards. But the backwards one has this additional dependency on the forwards input. It is extremely non-obvious that you can make a category out of this. Well, identities are easy. You can go from x prime to x prime. We need to go from x to x, that's the identity, and we need to go from x times x prime to x prime. That's going to be the second projection. But it's not so easy to figure out how you compose these things. So let's say we have another one. We have a g from y to z, and we have a g prime from y times z prime to y prime. So we want to compose these things to give, and I should say, the pair of these two things is called a lens. So this is an example of a category that I've named after its morphisms. So we have a lens from x prime to y prime, and one from y prime to z prime. We want to compose them. So first of all, we need a function from x to z. Well, that's easy. We can go x to y to z. But now for the tricky thing. So we need to go from x, z prime to y prime. So let's do this by kind of type-directed programming. So we have an x, and we have a z prime. And we need to get an x prime. How do we get an x prime? Well, the only way we can get an x prime is that it's f prime of something. So now we want an x and a y prime. Well, okay, we have an x, so that's okay. Now we need a y prime. How do we get a y prime? Well, we can get one from g prime. So it's going to be g prime of something. And now, okay, so now things get a bit tricky. So we need a y and a z prime. Well, we have a z prime. We inputted one of them. But we also need a y. How do we get a y? Well, it's f of something. So suddenly everything involved so far was primed. But so let's say it's the backwards part, but this depends on the forwards part. So this is going to be f of x. That's our thing of type y. So this defines the composite. You should be skeptical that this forms a category. So to be a category, morphism composition has to be associative. It is extremely not obvious that this is associative. There are some big brain ways of seeing this, but the easiest thing is to mangle the algebra for about 5 lines, just do a quick equational proof. But it's I don't really know an intuitive way of seeing why this composition operation is associative, but it is. So this thing is a category. Okay. And in fact, we can generalize this from set to any category that has finite products, pairs of objects of C. So C needs to have finite Cartesian products. Since I talked a bunch about supplies of comonoids, we have a bunch of examples of categories where you can copy data, but you fail the universal property of being a Cartesian product. Like all of your Kleisli categories of commutative monads on set allow you to copy data, but they're not Cartesian. You might think that I can make a definition like that there, and then you would make the same mistake I made in my PhD thesis. This is not actually true. There's a definition which type checks but fails to be associative. So you really need C to actually have finite products for this to work. There is a way of making this definition work for a merely monoidal category, and I'm going to tell you about that later, but it's even less obvious. Why do we care about these things? Basically because there's heaps of examples of these things. So I basically built my career on noticing examples of this pattern all over the place. I just point at things and say it's a lens. Um, if you follow me on Twitter about 4 years ago, this was a meme um, before the great collapse. Um, um, okay. So, what order should I do things in? I think I'll give some examples of these things as motivation, and then I'll go back to talk about the monoidal structure and draw some string diagrams. Because this is a pretty, it's not an abstract definition as such. It's just a very strange-looking definition. It's like it's not like a natural definition in some informal sense, in the informal sense. The place where these first appeared was in database theory and functional programming, where you're talking about destructive updates of data. So suppose you have some data type, and then you have some notion of deltas on that data. I'm gonna write delta x. So delta x is some notion of a change to values in x. But the most basic thing that you could say is that the change is just we're going to override it with a new value. So the original version of lenses was like this. We just say we have an old value and then a destructive update with a new value. And so a lens from x and deltas on x to y and deltas on y is something like, so it's a function from x to y, equipped with a way that says if I do a delta on the output, then I can get a delta on the input. So this is a kind of bidirectional. So this is called a bidirectional transformation. So actually, to simplify, let me say a delta is a delta is just a new like we're going to replace it wholesale. We're going to forget the whole, throw away the old value, replace it with this new one. An example of one of these is suppose x actually factors as the Cartesian product of y times some other stuff, which I'll call it C for complement. That's what it's traditionally called. So a lens like this, we need to have a function from x to y, and that's going to be the projection from x onto y. And then we need a function x. So x is y times c times, so that's the old value times a new value of the y part, and then we need to give a new value on the whole. And then the idea is that, so we start off with something of the form yc, and then we are given a new value for the y part, and then we send it to y prime c, and we throw away the old part of y, but we keep the old part of c. Okay, so this is like the classic example of a lens. And the thing is that the composition law I told you respects this. So what this is used for in functional programming is for doing destructive updates in deeply nested, like, complex data types. So you have some big data type that's defined in like several nested levels of definition, and you want to say, I want to kind of project out this value through several levels, but in a way that allows me to do a destructive update to it. So actually, this structure was discovered independently multiple times, but one of the discoveries, the original appearance of this in functional programming was motivated by the question of suppose we have a language like Haskell that strictly guards side effects with its type system, and we want to do a very state-heavy application such as a video game. So we're running some kind of game loop 60 times per second, and we have some gigantic data structure about the game world, and 60 times per second we want to do these kind of complex stateful updates to this data structure. So the traditional way to do this in Haskell would be with something like the ST monad, but this is a more disciplined way of doing it. So these are actually, well, They are used in industrial Haskell. They have some downsides. It's complicated, but these things are actually used. Okay. Infamously, the source code of Minecraft, which is written in Java, contains an implementation of these things. Okay, so that was the classic thing, but it turns out that this pattern actually appears a lot. So here's a totally different example. Suppose I have a smooth function f from, say, r to r, to keep it simple. And this is a moment where I accidentally talk like a physicist, because smooth means sufficiently differentiable for the thing I'm doing right now, which in this case means once differentiable. So this thing. So let's say we have some equation like y equals f of x, right? We can differentiate this. So dy dx is f prime of x. So I mean, I can give a concrete example of this. So let's say like y equals x squared. So now here I can say dy dx equals 2x. But now let's do the thing that your analysis 1 teacher taught you not to do. So I'm going to rewrite this to, how am I going to rewrite this? I'm going to write this as 1 over dx is f prime of x times 1 over dy. So this little trick, this is called reverse differentiation. So this is the basis of how backpropagation works in machine learning. So what I can do is I can make a lens from, so this is going to be f prime going from r to r. So in the forwards part, we need a function from r to r. That's going to be f. So we're going to have f goes from r to r, and in the backwards part, I should not have called this f prime. I'm going to call this df. Hopefully that's not confusing. I'm not. Okay, fine. Okay, I'm going to call it f sharp, which is what a sheaf theorist would call it. Because the same structure keeps getting discovered by different groups of people. This is the sheaf theory version. This thing is like a morphism of sheaves between cotangent bundles. So f sharp, which is some function r times r to r, this is going to go from x together with something which is going to basically mean 1 over dy. I'll call this like Hurley dy. I'm not sure what I should call this. I forgot my differential geometry. There's a technical term for the kind of thing this is. I think it's a one form, but I'm not a differential geometrist, so that might be wrong. And I'm going to take this to f prime of x times dy. So that's what the corresponding thing you would call dx. Yeah. So I defined a lens to be a pair of functions. So this is its type as a lens, as a morphism in the category of lenses, but it's made the data that defines it is a pair of functions. Yeah. No. This one's f prime. So this is the actual derivative of f. So for example, if I took my squaring example, this would be x goes to x squared and this would be x dy goes to 2x times dy. Okay, like this is the kind of differential geometry thing, is that if you're slightly careful about linearity and things like that, these things are just functions. Like you can treat infinitesimals as ordinary values. You just need to make sure that everything is correctly linear. Okay, now, yes. Yes, so I'm basically saying that like dy means 1 over dy. And actually, I'm also papering over a really subtle point where in machine learning they take transpose rather than matrix inverse, because matrix inverse is way too slow. So, and I've done this for single variable functions, but all of this works for multivariable functions. And this thing has to be the Jacobian, which is the matrix of all partial derivatives, and everything is very complicated. And I can't assume that everyone has the necessary background in linear algebra for this. But this is like a semi-formal version of what's going on in machine learning. So the magical thing is that okay, so what am I actually doing here is I'm associating differentiable functions. Given a differentiable function, I'm building a lens. And what this actually is a functor from, so a long time ago I said I'm going to have a category of Euclidean spaces and smooth functions, where smooth means differentiable enough for what I'm doing right now. So what I'm building is a functor like this from Euclidean spaces to lenses. And the important point here is functoriality, because the fact that this is a functor is the chain rule. This is actually how differential geometers state the chain rule, with different words. So what this is saying is that if I have another function here, so I can do two different things. I can either compose them as smooth functions, so I have f then g, and I can then differentiate that and do this construction, or I could differentiate them individually and then compose them using the definition of the lens composite. And the fact that those things agree with each other is the chain rule. So in other words, so what does that mean? It means that f then g prime of x is, see if I can get this right, f prime of, I'm never going to get this right. Okay, don't worry. This one I haven't written in my notes. I'm never going to get the reverse chain rule right if I try to write it down directly. You have to trust me. That's equivalent to is like the same thing on the nose as functoriality for this. Okay. So basically the observation that so this is specifically called the reverse chain rule because it's for these kind of inverse derivatives that go backwards. There is also a forwards chain rule. Yeah. 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 The observation that the backprop algorithm. So this is how neural networks work. This method exactly matches lens composition, which has come from this completely other field to do with data updating, was basically the observation that sparked what we now call categorical cybernetics, which is a field where we point at things and say it's a lens. And then also try to exploit that fact that this same mathematical structure appears unreasonably often. Yes. Okay. Is that everything I want to say about? So I'll say a little bit about how a neural network works. So a neural network is basically a function that has a very specific form, that it's made of a composite of a finite number of layers, and each layer consists of an affine function, so matrix times input plus matrix times input plus vector, and then apply a fixed for all time nonlinear function to it. The most common one in practice is that one. So identity on positive numbers and const 0 on negative numbers. That's machine learning people call that ReLU, rectified linear unit. And then, so the idea is now that your matrix, so your fixed nonlinear function here. So f is fixed, but m and v are parameters in this. And then the goal of training a neural network is to optimize m and v in order to make this whole thing behave, or to make a composite of a whole bunch of these sequenced end-to-end behave in a particular way. And how you do this is by backpropagation. So you have an input, and then at the very end you have a derivative which says how you would like the final output to move. And then you apply this method to kind of step this derivative back layer by layer. And this functional form is designed so that each individual step of that is extremely efficient. Yeah? It forms a functor going to a different category that's not lens. I'm not going to talk about that. There's something interesting there, but I'm not going to talk about that. Otherwise, we'll be here all day. Okay, I'm going to give another example, and then after one other example, I think I will have sufficiently convinced you that this structure appears in lots of places. Let's talk about Bayesian reasoning. So, suppose we have a probabilistic function from x to y, so a Kleisli morphism of probability. I'm going to imagine this as a kind of probabilistic black box. So I have a machine. I can stick in inputs, and I get outputs. And the output I get depends on both the input and on random chance. A probability theorist, if they were being extremely careful, would write this as something like probability according to f of y given some x. Now, suppose we're in the situation that we can see the output of this machine, but not the input. The problem of Bayesian reasoning, or Bayesian inversion, Bayesian inference, is basically to try to infer what the input of a probabilistic function was given its output. In order to do that, in general, we need to have some initial belief about what the input was. This is called a prior. And then there's a formula called Bayes' law, which gives you, basically says how you should optimally update your prior in order to account for the new evidence of the outputs that you've just seen. So what we're going to do is we're going to have some distribution on x. We'll call that pi. So this is pi for prior. This is our initial belief about what this is. So if our belief is correct, the distribution on the output that we would expect to see is f of pi. And here I'm being sloppy with notation. This is a Kleisli, like we Kleisli extend f along this monad. Right, you can give a probabilistic input to a probabilistic function. And in fact, so where the probability that the probability of some y according to the prior is the probability of some x according to the prior times the probability according to f that we get y if we had that x, and then we need to sum over all of the x's in general. So if we're in a finite support world, like I've kind of assumed here, then this is just a sum over finitely many values. Now, Bayes' law now says, so if I observe some particular value y that's output by this thing, what should my new belief about the distribution of the input be? And there's a particular formula for that. It's how am I going to do this? It's okay, maybe it's best if I don't say what it is, because I'll also screw it up. This is why I normally give this talk with slides, because there are like actual classic formulas to remember in this version, in this talk. But trust me, there is a standard formula. So what this means, so what we get in the end is a thing which I call the Bayesian inverse of f, and I'm going to write it as f dagger, and it's defined given pi. So I'm going to write this as f dagger sub pi. This is a probabilistic function that says if we observe some y, what should our new distribution on x be? So this thing is actually is a Kleisli morphism of delta as well. And so I asked the question once, does this satisfy a chain rule? Because we know that this thing, like these things form a category, we can compose them. If we have also some, so this is like saying, suppose we have a setup where we have a probabilistic machine that turns x's into y's and another probabilistic machine that turns y's into z's. And we have a belief about the distribution of x, and we observe the output of the entire pipeline. Does this satisfy a chain rule? And I say a chain rule, not the chain rule, because there's no calculus here. There's no differentiation, but it's something structurally the same. Can I kind of backpropagate my beliefs one step at a time? And Toby Smythe went away and proved that yes, you can do this. This is actually true. So. In other words, the Bayesian inverse of f composed G is given by the Bayesian inverse of G for f of pi followed by the Bayesian inverse of f of pi. That's the probabilistic chain rule. So this says that we have a functor from. So this is functoriality. So like at that point we're like, okay, there's an actual idea here. Like this structure is actually really common, and there's more examples. I think I've given you like the most important examples, but there's like this pops up all over the place. Okay. So this is basically my motivation for why we care about lenses. Is that there's tons of important examples. Yeah.
Delta, which one is again?
This is probability. So I'm being sloppy here. So this means some probability monad. Actually, Toby proved this generically in a Markov category. So so this is actually true in a very, very wide range of interpretations of what probability means. This is a robust result. This doesn't rely on any like weird quirks of measure theory or anything like that. Which is also nice. Like, if you wanted to prove this measure theoretically, it would be an absolute nightmare. So proving it generically was actually better. And then the fact that somebody else had already proved that measure theory gives you a Markov category means that these, yeah. Okay. So now I want to talk more about the categorical structure of lenses. So hopefully I've motivated you that there are reasons to do this, that there are important things that we care about that are structured this way. So lens C is, so this thing has this thing has several. Okay, it has a couple of monoidal products. It has a Cartesian product, which is given by product in the product of the objects that are in the forwards direction and co-product of the objects that are in the backwards direction. That turns out to be a Cartesian product. Yeah.
So I don't think lens was part of right range before.
This is so C is a category with finite products. So you can do this lens construction over any finite product category. But you can pretend that C is set, and everything I say is still true. So it has Cartesian products, but there's a different monoidal product, which is the one that you virtually always want. So on objects, we say that, so we want to take the product of some object, x prime with some object, y prime. I'm going to say it's pairwise Cartesian product. So x times y, x prime times y prime. And trust me, you can extend this to morphisms in a completely straightforward way. So this turns out to be a kind of very interesting monoidal product. For one thing, this means that every object splits into a kind of purely forwards object and a purely backwards object. So that's a bit weird. Like most monoidal products don't have factorization like this. So this motivates me drawing string diagrams for this thing. So instead of saying that we have some lens, I'm going to say lambda for lens, from x prime to y prime, instead I'm going to say that it goes from x prime to y prime. So I actually draw these things with directed arrows where the forwards direction is pointing forwards and the backwards direction is pointing backwards. So this was completely motivated by the notation for non-self-dual symmetric monoidal categories. Now, here's an interesting observation. For every set, or rather every object in my category, I have a morphism going from x to 1, 1. And 1, 1, so because the Cartesian product, sorry, the monoidal product is pairwise Cartesian product, so its monoidal unit is 1, 1. So I'm going to write I, but I means the pair 1, 1. Here 1 is either the set with one element or it's the terminal object of C, like the nullary product. So I claim that we have a canonical one of these, which I'll call epsilon, because for reasons that will become clear in a minute. So this thing would have to be made of a forwards pass, which goes from x to the forwards object of this, which is 1. And we have one of those because x is terminal. 1 is terminal in C. And then we need a backwards pass, which goes from x times 1 to x, and this thing's isomorphic to x, right? So this is the identity. This is the identity up to some isos. So what this means is I'm going to draw this like this. So this is going from, you can kind of read off, this is going from the object xx, that's forwards x and backwards x, to the monoidal unit, which is empty space. That's a forwards empty space and a backwards empty space. And this kind of behaves nicely. So I can embed, so I'll tell you the basic property this has, which is actually naturality or dinaturality. So I have an embedding of C into lens C, which takes x to x1 and takes f to the thing which is f forwards and identity on 1 backwards. I also have a different embedding of C up into lens C. This is, I'm saying that lens C is a lot like C times C up. This is a property that C times C up also shares, that you have an embedding of C and an embedding of C up. So this is x goes to 1, x. And these things all commute with each other. So what that says is that if I have a function that was purely forwards, it's the same thing as, that's f. Oh, right, this is f star. That's the contravariant embedding. Okay, so this thing has this kind of nice properties which it shares with. So it shares this with compact closed categories. A lot of on compact closed categories, everything topologically does the thing that you think it should, essentially by definition. Whereas here you have to carefully check it. Right, this is a lemma. But it turns out that unlike compact closed categories, we do not have a corresponding morphism the other way. So to go the other way, we would have to start by having a forwards function that would go from 1 to x, and we just can't do that. So whereas compact closed categories are kind of fully symmetrical, here we have a broken symmetry. The forwards pass and the back. I mean, you could see it when I wrote the definition of lenses. This is a very strange, lopsided definition. So this is the consequence of that. So what we get is a language of string diagrams where we have directed arrows, and we can turn our wires around this way, but we can't turn our wires around this way. It transpires that the category of lenses actually has a universal property that it basically amounts to. It's the universal category that is like that, which is very strange. Is that a question or a stretch? Cool. Cool. That's 3/4 through. Now I'm going to tell you about, oh my God, it's so hot in here, I'm sweating. I'm going to tell you about 2 different generalizations of this construction. So first I'll talk about optics, and then I'll talk about dependent lenses / containers / polynomial functors. So I'll end on something that involves dependent type theory to come back vaguely on topic to everything else. Yeah? Yes. Now I feel like a performing monkey. You can turn things around this way, but you can't turn things around this way. And like interpretive dance is left as an exercise for, yeah. Okay. So everything I've said so far works for a category of finite products. It turns out that you can do a huge generalization of this, and this works for any monoidal category, but it's super non-obvious how to do this. So now C is going to be a monoidal category. I'm going to say symmetric monoidal, it doesn't really matter. It's SMC. What am I doing? It's a symmetric monoidal category. And now I'm really assuming that C is merely symmetric monoidal. The kind of categories I do this construction on tend to be not much more than that. Okay. We can build a category which I'll call optics, and now I'm not responsible for this terminology, but all the terminology around here is full of puns. So objects are going to be the same as in lens C. So objects are going to be pairs of objects of C. And so morphisms from x prime to y prime are going to be triples of an M, which is an object of C, an F, which goes from X to M tensor Y, and an F prime, which goes from M tensor Y prime to X prime. So the idea is that the backwards part, instead of receiving the forwards input directly, it receives it mediated through this object M, which is also given to you by the forwards function. And if your monoidal category is not Cartesian, these are like entangled. This thing does not consist of like an M given X and a Y given X. These things are like, you can't separate this out. Anyway, it turns out that this thing does not form a category, but it does if you quotient out a big old equivalence relation, which says that, so, here's the picture. So we have, so here, so everything above the midpoint is like a string diagram going from left to right, and everything below the midpoint is a string diagram going from right to left. So we have some F which goes from X to Y tensor M. Don't worry, it's fine. The ordering's fine. And then an F prime which goes from M tensor Y prime to X prime. And the equivalence relation we need to quotient out is the one generated by saying that if my F happens to factor like this, it should be the same as the optic I would get from the F prime, which was factoring like this. That turns out, that quotient turns out to have a universal property of its own. This thing is called a coend. I don't know if Chris mentioned these, but it's like one of the it's one of the universal properties along with colimits and Lefkan extensions. These things are all, like in pure category theory, these things are all interdefinable. So we write this as, we write the set of these things, the set of equivalence classes as integral M C X M tensor Y, that's the Helm set, times C M tensor Y prime, X prime. So, and the reason we do this is because the properties that this coend, this set of equivalence classes satisfies, is all of the properties of integrals in calculus. It's extremely magical. So there's a thing called coend calculus. So Fosco Leregian wrote a book about this, which is the biggest lifesaver in the world. This whole field just wouldn't be possible if it wasn't for this book, because everything was so folkloric before that if you weren't Australian from the 70s, you just didn't know how to do this. Yes. It did not. So it's a letter H. So basically, I'm saying that the triple of M F, which happens to factor in this way, and F prime. So this is M prime, M, X, Y, M, Y prime, X prime should be equivalent to M prime, and then I move this morphism over to here, over to there. So it's that and that. Yeah. Thank you for the leading question. Yes, if you're in Haskell or anything like it with a polymorphic type system, you can write you can write. So this behaves like this doesn't behave like a sigma. This behaves like a polymorphic types exists. Thank you for the leading question. Yes, yeah. So coends a bit strange, but they behave like existential types in like most ways that matter. Okay, cool. So this is a big scary definition, and here is the important lemma. If C is Cartesian monoidal, so if your monoidal product is a Cartesian product, then these agree. Then optic C is isomorphic to then C as a category. The isomorphism is identity on objects, but you have to do some quite non-trivial stuff on the morphisms. The proof of this amounts to the Unay dilemma. So this is a non-trivial proof. It's one line of coend calculus, but the coend calculus is an extremely powerful tool that encapsulates the Unay dilemma in a very simple way, a way that's very simple to use. I'm not going to talk about this. That would be a different talk. Cool. So what this is, this is the correct definition. Okay, I make a claim there. This is an informal claim, but it's true. This is the correct definition, the correct generalization of lens C from a finite product category to a merely monoidal category. So this says that we can do this construction on any monoidal category. And it transpires, this is also not obvious, but it transpires that even if you are Cartesian, this is a closer operational description of what the backprop algorithm is doing operationally. This is a bit strange. I'm not going to go into details on that, but the M you get is what in differentiable programming or in backprop is called the tape, which is a data structure which is used for communication from the forwards pass to the backwards pass. Okay, cool. Yes.
When you say operationally,
I'm being very, very informal here. So I don't mean in operational semantics. I mean it's a vibe. Mm-hmm. I mean, you can sort of look at it and see that this basically matches what they're doing. Mm-hmm. Yeah, no, that's an informal claim. That can probably be made precise, but that's a research question. Okay, now I'm going to talk about dependent lenses. So suppose we have this definition. So I'm going to go back to the Cartesian definition of lenses. So we have okay. So and now I'm going to do this over set to make life easy. So we have 4 sets: X, set. If you were, let's say, an Agda programmer, or an Idris programmer, or a Lean programmer, or whatever, and I asked you to write this down, you would be sorely tempted to add the missing dependent types that can be trivially inserted here. So you can completely straightforwardly say that X prime depends on X, and Y prime depends on Y. So in other words, X is a set, and if X is in X, then X prime is a set. And now, so F is still a function from X to Y, and F prime, I'm just going to curry this to unify the notation. So this would now say that this would be a dependent function that if I have some X, then and I have a Y prime, which would be indexed by F of X, then I can get an X prime indexed by X. So I call this thing a dependent lens. So this thing also has multiple terminology. So I call this a dependent lens. So these things also form a category, right? You can write this in any dependently typed programming language. The categorical structure you need in order to do this semantically is that you need a category with finite limits, but it helps if you're locally Cartesian closed, which makes your model of enough type theory to not have to worry about things. Nobody's talked about locally Cartesian closed categories. That's okay. They're very scary. Don't worry about it. They're models of dependent type theory with sigma and pi. Yeah, they're models of sigma and pi. So in other words, you have dependent functions. Okay. This thing, so it turns out, so again, this thing was developed independently several times. This thing is often called a container. And there's a series of papers. Thank you. So there was a series of papers in the 2000s by people who, at the time, were in Nottingham and now are in Strathclyde, on the category of containers, which is the category whose objects are these things and whose morphisms are these things. So these things are also called container morphisms. And why would you want to use these? Well, it's completely obvious, right? Because if you want to use lenses and you want to get all of the benefits of dependent types, that's what you want. Also, if you want to do calculus on like non-flat manifolds, but that's complicated, so I'll leave that to mathematicians. Okay. And so here is a extremely magical theorem. The category of so I'll write this as containers and this is why I like this notation. This is the category whose objects are containers and morphisms and dependent lenses. Now I can use different terminology for coming from different places and still write what I mean. This category is, in an extremely non-trivial way, equivalent to the category whose objects are polynomial endofunctors and morphisms and natural transformations. So this category is called poly. So right now we have a big divide across the Atlantic Ocean where people on the East Coast use this and people on the West Coast, or in fact on the West Coast of the West Coast, this is David Spivak and collaborators do everything with this. But they are equivalent categories. They are the same thing. They are the same thing in a highly non-trivial way. The proof of this also involves Unada in a more scary way than the last time I mentioned. So David and collaborators have been working like crazy, developing all kinds of crazy things you can do with this. And those things are also applications of lenses. Okay, it's 29 minutes past. I think that's oh, okay. I'm going to mention, this is a perfect opportunity to mention, so we have lenses, we have optics, which is a generalization of it, we have dependent lenses / poly, which is a kind of specialization of it when you have additional structure for dependent types. How do you unify these things? Because there's a split between kind of people who do applications of these things and people who do applications of these things. And these are really different structures, but they were motivated as generalizations of the same thing. This question kept us busy for 3 years. This was a very, very difficult question. This is, if you ever heard me talk about dependent optics, that's what I mean by dependent optics, is what is this? And if I had another 2 hours, I could explain that, but I don't. So that's me.